we're going to do a maximization problem without using calculus. Now, I happen to think using calculus is actually kind of hard on this problem because you actually, taking the derivative is easy, but then you end up with two fractions, square roots in the denominator, and it seems kind of difficult to do the calculus there. You know, the idea is to take derivative set equal to 0 to find horizontal tangent lines. And I'm sure it's doable, but I found it kind of messy. So this Cauchy Schwarz inequality turns out to be quite useful. Now, what I'm doing here is actually a college algebra problem. I'm writing down the domain of this function, right? You can see that if you pick a number to the left of 9 over 7, for example, 1, you would have a negative radicand right here. And a number to the right of 2, you would also have a negative radicand right here. So this is the domain of this function. You don't necessarily have to write this down to find the maximum, but I think it kind of yields a little bit of insight. Okay, so now, y'all, we are using the Cauchy Schwarz inequality. I like to think of this as the inner product squared for like an n-dimensional vector, you know, and we'll be doing it for the case n equals 2, as you can see down here. Now, I've rewritten it just a little bit, but again, this is for the case n equals 2. N equals 2, and it's really kind of nice how it works out. It's very, very clean. Now, so it's useful here to think of a 1 being in front of this, right? So I'll put a 1 dot right here. All right, and that's exactly where, there we go, it's a little neater right there. All right, maybe let's put the 1 here, okay? So 1 times. Now, a lot of you just, you know, it's kind of a crutch, but I like just being explicit. So you can see exactly where everything's coming from with the a sub 1s, b sub 1s, all right? And so this works out fairly cleanly, like right here. Notice it's designed to where the x's cancel out when you square. And so what you end up with is less than or equal to the square root. That's 5 squared is 25 plus 1 is 26. So we have 26. Okay, 26 is what this piece right here evaluates to. So you have 26. Okay, and then you would have minus 9 over 7 plus 2. Okay, notice that the x's go away, so you'll have minus 9 over 7 plus 2, which is what? Minus 9 over 7 plus 14 over 7, which is 5 over 7. So I'll write it like this. 5 over 7. Okay. And what do we get? That's equal to, let's see, folks, this would be 130. So I'm just going to write it. It doesn't make any difference, really. You don't have, everybody makes a big deal about rationalizing. But you can just write it as the square root of 130 over 7. Okay, y'all, without hardly lifting a finger here, this is the answer. Square root of 130 over 7. That's the maximum value. Now notice the instructions just call for finding the maximum value, but you could also use this condition right here. Equality occurs when these vectors are really just the same vectors, I think, when they're proportional. And so in this context right here, you could just set, you could think of it like this. You can write the square root of x. And I may be writing it upside down with respect to the letters, but it's okay. If fractions are equal, their reciprocals are equal. So you can think of x minus 9 over 7. And y'all, what we're trying to do right now is actually find out what the x value is when this maximum value occurs. All right. So x, square root of x. And again, just for emphasis, I'll put over 1. So you'll see we're equating these ratios. And right here you would have the square root of 2 minus x over 5. Okay. And again, y'all, that lines up with the equality condition up here of your quotients or your ratios being equal to the very same constant. You can think of them as being points on a line if you want to. Okay, but that's this equality, this proportionality leads to the equality here if you go through the proof of Cauchy Schwarz. And so that's exactly what I've done right here. Now, if you square away right here, I won't work through every bit of the algebra, But if you square array right here, you would get x minus 9 over 7. Okay, equals to 2 minus x over 25. Okay, now y'all, I'll go ahead and just write down the answer. This is fairly straightforward mathematics right here, just it's fairly easy, but I'll just write down the result here. What you would get right here is x is equal to 239 over 182. So the maximum also occurs. This was what would be happening in calculus if you set the derivative equal to 0 and you solved, you would get x is equal to this value right here. 239 over, I guess they would call this a critical number in calculus. But anyway, this would be where you would have a horizontal tangent line on the graph, the x-coordinate of a horizontal tangent line. Okay. Now, so that's 239 over 182. When the expressions take on, when x takes on this value, the sum of those two radicals, the sum of these two radicals actually maxes out. In other words, when you put x equals to that 239 over 182 here and here, you would actually get the square root of 130 over 7. Okay. Now notice though that that's let's see here, this 9 over 7 that we did for the domain. What's 9 over 7? Let me see if do I have room here? I'll write down 9 over 7. What is that equal to? I'm trying to get the same denominator with 182. So that would be times 26 over 26, right? Okay, and what do we got here, folks? Let's see if I can handle this. 9 times 6 is 54, 234. So that would be 234. See, yeah, that caught us. Yeah, I was just checking. Yeah, 234 over 182 when you do the arithmetic here. 7 times 26 is 182, so you get 234 over 182. This isn't a necessary step, but this is the fractional equivalent of this left endpoint, right? But notice that we had 239 here, right? We have 239 over 182 right here. So that's contained. This is definitely contained. This is a member of D. We'll call, you want to do it like this. Member of the domain. Do I actually have room here? Domain. And it better be a member of the domain. Barely had room, folks. So anyway, but y'all, this is the final answer. I love this stuff. I think it's cool how Cauchy Schwarz just nails this to the wall, really. It's pretty easy. The notation's a little bit of a headache sometimes. But anyway, I enjoyed that problem, and I hope you did.